All right, hi everyone. So today I'm going to tell you about building abstractions into deep learning models in order to achieve better generalization. When we talk about low resource settings, generalization is key to typically how we try to solve problems. So one canonical approach to handling these settings is we have a lot of data in a high resource setting, we train some model, and then we have some either small amount of data or domain knowledge or something to bring to bear in our low resource setting, and we take that model and we adapt it to that low resource setting. All right, implicit in this is the assumption that from the high resource setting, we can learn something sort of universal, some kind of core linguistic phenomena that will help us in the low resource setting. All right, so how do we go about measuring whether or not our models can do this? So the way we typically evaluate how strong our models are is by looking at benchmark data sets. So in a lot of the how we approach problems in NLP, there's this implicit assumption that having higher leaderboard numbers means that we have overall better models of language. Okay, so if we look back at the history of something like, say, English pen tree bank parsing, we can sort of evaluate whether or not this claim holds. And if we look here, there's sort of an implicit leaderboard here in the literature taken from Petrov et al. 2006. And what we see is that as numbers got better and better, there was kind of big ideas in improving modeling of parsing that contributed to this. For example, relaxing context-free assumptions, latent variable modeling to capture things like subcategorization, lexicalization, re-ranking, et cetera. So when we got better numbers in these settings, they actually typically did mean that we had more general models of language because they did transfer to settings like the Brown corpus, web tree banks, or other languages. Okay, so I'm going to roughly say that this claim was true in 2006. In 2019, I think many of us feel that there is now a different story. And so there's increasing evidence in the literature for why this might be the case. So one reason is that our tasks and data sets sometimes just aren't set up right. For example, we're dealing with things like annotation artifacts in our data. Our models are learning to fit surface patterns and not the deeper linguistic phenomena that we really want them to capture. We also sometimes set up tasks for things like, all right, let's build a question answering task where you have to look at multiple sentences to find the right answer, but then it turns out you can get the right answer with only looking at one sentence. The other reason is just standard domain overfitting, but neural nets have made it better. So for example, Mousavi and Strub have a nice paper showing that neural coreference systems underperform when transferred to new settings. And recent work from Talmor and Barant shows that QA models often don't transfer even between related settings. So there's a lot of work to be done on the data side of this. But what I'm going to talk to you about today is whether there's ways of restructuring our models to do a better job of this. So the standard deep learning paradigm that we're looking at often looks like this, where we have an end-to-end neural model going from input to output. And what I'm going to propose in this talk looks more like this, where we now have this intermediate abstraction that we're trying to predict here. So this is introducing a form of modularity into our models. We're structuring the process, as depicted here, into two stages. And these stages aren't necessarily going to correspond to conventional NLP pipeline tasks. And we're going to see why that is later. So what are the advantages of this framework? Well, one of them is that we are going to, in our approach, maintain some uncertainty over our abstractions. So we're going to be able to reason about different analyses of the original text and not have to commit to something in advance like traditional pipeline models do. These abstractions are going to help us impose inductive bias. So the annotation artifacts that we might be worried about fitting are possibly going to be mitigated if our models just aren't able to fit them as effectively. We also believe that if modules solve particular subproblems, we may be able to take those modules and isolate them and transfer those to other domains or other settings better than a full end-to-end model, where it may be hard to disentangle the pieces that transfer from the pieces that don't. And then finally, we can reason about and understand these intermediate outputs that we're dealing with here. All right, so today I'm going to tell you about two instantiations of this. The first is going to be some work on entity linking, with the abstraction being fine-grained entity types. And the second is going to be some work on regular expression synthesis using sketches, which are coarse representations of a program's semantics. All right, let's dive into the first one of these. So this is work on entity linking done by my student Yasumasa at UT. So how do neural net models for entity linking work? Well, let me give you a kind of canonical picture of this. So we have a mention in context. Like in the late 70s, I remember watching A Star is Born and really enjoying it. And then we have some entities in a knowledge base, like the two different years when this movie was released. And we want to pick which of these is the correct mention in this given context. All right, so true to form, our neural models are going to do something like embed the mention in context into a vector, embed these entities into vectors, and then do some kind of comparison between these things. So this process is fairly flexible. There's a lot of different models that fall into this framework, but a lot of them have the problem that there are enough parameters in this approach to overfit not just a domain, but the particularly entity distribution in a data set. So for example, this might arise from the fact that we might have very complex and highly parameterized operators for doing this comparison step, or in some cases, we even have trainable parameters associated with each of these entities, and so the model is just going to learn what's in the training set, but won't really generalize to new entities. And so we can see this in one recent data set, WikiLinks NED, because if we look at the performance of the models, it actually drops by 20% if we train them on Wikipedia instead of the in-domain data. So clearly, we're not getting the right generalization here, and there's a number of reasons for this, but one of them is this entity overfitting effect. All right, let me tell you about a different approach for doing entity linking that's going to mitigate this. So let's take a look at this example. Dell is headquartered just outside of Austin. Maybe an entity linking system doesn't know whether this refers to Michael Dell or Dell the corporation. But fortunately, this is the kind of distinction that NER systems are great at making, right? This is just person versus organization. We've had models for 15 years that are pretty good at this task. And so using those, we can rule out the person label here, and we know that it's the organization. All right, this gets a little trickier when we look at the example that we just had. So in that case, we had two films in 2 different years, so they're going to have the same coarse-grained NER tags. The answer to this that we're going to explore here is to use very fine-grained NER types, inspired by some work from Unsel Choi and co-authors from University of Washington, where we have many different types, and these correspond to very specific properties. So for example, you might have each of these films associated with a particular decade. And now we have a fine-grained enough type system to be able to make this determination. And I think this intuitively makes sense with how we think about this. You might say, oh, no, I'm not talking about the movie that came out last year. I'm talking about the one from the 70s, right? This is kind of inherent in how we refer to these things. So these are going to be sufficient to reason about even very nuanced distinctions that we're trying to make here. All right, so here's how our approach is going to work. So we're going to take our mention in context, and we're going to put it through an entity typing model and produce posterior distributions over types, which are binary random variables for each type in a large vocabulary. So here we might recognize that this is highly associated with 1970s in film, and maybe there's some other types that have reasonable posterior probabilities as well. But this is a soft typing, essentially. We don't commit to an analysis at this stage. Then we have our knowledge base entities, and these also have associated types. And now, in order to do this comparison, we can just use a relatively simple heuristic, like taking the dot product between these two representations. All right, so the piece of this I haven't told you how to do yet is where we get all these types from and how they get into our knowledge base and where we get our typing model from. So this is all going to come from Wikipedia. So there's been lots of past work in especially NER using Wikipedia categories as sources of supervision, and so we're sort of following in that vein. What we do is we take these categories and do a little bit of splitting on them. So for example, we split out prepositional phrases to kind of get sort of orthogonal properties and to introduce some new course types like people here. And then we keep around 60,000 categories for our prediction. This is also where we get our data to train our typing model. So we can basically treat Wikipedia as a source of distant supervision. So how that works is we look at a sentence like this, and it's got hyperlinks in Wikipedia. So we know that this reference to A Star is Born is referring to the 1976 film. We're not going to use that as training. Instead, we're just going to use the types. So we basically project that entity reference down to its types, and now this is some lovely data that we can use to train our typing model. All right, so I'll give you a quick tour of some results. So these are results on the Connell-Yago the standard NER data set, which has also had entity links added to it. Our model trains only on Wikipedia, not on the standard in-domain data. So we're only comparing to other models in that paradigm as well. And what we see is that our approach works in this setting, transfers from Wikipedia better than neural models, and also better than some past work and comparably to other systems which don't use the in-domain data. And we look at another setting which is even harder, this WikiLinks NED corpus that I mentioned, which is taken from noisy web text, and we look only at entities that haven't been seen in the training data of that corpus. So these are the entities in this data set were selected to be highly ambiguous. So we've got a very difficult resolution problem, and we're trying to check how we generalize to new entities. And what we see is that our approach is able to generalize, again, better than the neural models, including the neural model which we tested, which was state-of-the-art on this data set in the sort of standard setting. All right, so what are the takeaways from this? So coming back to this idea of abstractions, why were types a useful abstraction for this problem? Well, one reason is that we can actually predict them with some amount of accuracy. So even for rare types, our model is at least able to predict them correctly sometimes. And they're sufficient to do the end task. If we had stuck with coarse types, which we can predict with high accuracy, we wouldn't have had enough information, but going to these noisy fine-grained types is more useful. And why does this transfer? Well, I don't have a deep reason for this, but I think I'm going to sort of appeal to a Goldilocks principle, which is that if we use something like off-the-shelf things like NER systems to predict coarse types, that just doesn't give us enough information. And then modeling things at the entity level, well, there's millions of entities, even if we're using sort of flexible models, it's sort of not the right level of transfer, and this tens of thousands of types is kind of just the happy medium. All right, so I will say that there are plenty of limitations with what we've done so far. We've only looked at this for English, but we're currently working on generalizing it. There are some entities in Wikipedia where this doesn't work well, just because of how the category structure is set up. So we're trying to break away from that assumption and the reliance on Wikipedia's structure. But in general, I think that this is a nice path forward for leveraging high-capacity neural models for this task, but doing so in a way that's going to generalize better. All right, so now I'm going to switch gears a bit and talk about some work on regular expression synthesis from natural language. So this is in collaboration with some folks in programming languages at UT Austin. Jocelyn Chen, my student Xie, Xinyu Wang, and Ishil Dillig. So what regex synthesis is about is basically we have a string here which describes an intent that the user wants to be able to recognize certain lines in a file. So they say lines starting with a capital letter not containing the string dog. So this is taken from a data set from Locascio et al. From MIT. And their approach was to use a sequence-to-sequence model for this. So they have a lot of data, they train a seq-to-seq model, and it can produce something which looks like this, which this doesn't look like your standard regex, but it's in a domain-specific language, which is equivalent in power. And so you might believe me when I say that these models can work pretty well for this type of data, right? So not contain the string dog, and then we get this not contain dog. Seq-to-seq models can do this kind of translation with some accuracy. So how does this work in practice? So our collaborators basically looked at posts on Stack Overflow where users were trying to synthesize regular expressions for real scenarios. And so they saw language like this. The input will be in the form a colon-separated tuple of 3 values. The first value will be an integer, with the other 2 values being either numeric or string. All right, so we've got lots of stuff that wasn't present in that previous example. We've got complex referring expressions. We have new kind of abstract constructs, this colon-separated tuple thing. If we look at other examples, we get things like ungrammatical language, and we get ambiguity also. So in this last example, I want this value to accept up to 18 digits before the decimal and 1 digit after, with the decimal point and the digit after it being optional. There's some questions here. As specific as the user tried to be, maybe we don't know, is it okay to have 0.0? Or can you have a decimal point, just point and then nothing, right? So when we train a model on this big labeled regex data set and try to run it on Stack Overflow, it actually gets none of these correct. They're just way too far along the complexity axis. The model just cannot generalize to things that look like this. It hasn't seen this type of language before. And so it would be wonderful if we had 100,000 of these that we could scrape and train something on, but unfortunately that's just not true. However, we do have something we can leverage, which is that users often specify the semantics of what they want, not just with language, but also with some examples. So for example, in this case, the user wrote in their post that, all right, I want the regex to match these things and not these other things. So this helps clarify the semantics a little bit. We see that 0.0 is OK. There are some things it still doesn't clarify. The view from the program synthesis folks is that the right thing to do here is then to interact with the user more via examples to further refine what they want and help them work toward the solution kind of collaboratively. All right. Regardless, what we want to do here is we want to leverage both these examples and natural language. And so that's what our framework of abstraction is going to allow us to do here. So we are going to have an intermediate representation here, which we call a sketch, which is a underspecified representation of the final program. And we're going to produce this from the language using a semantic parser, and then we're going to use a program synthesizer that takes this sketch and our examples and does search over the space of programs and finally outputs a concrete regex, which is designed to be consistent with the examples as well as the original natural language. All right, so what do these sketches look like? Well, they capture both high-level program structure and also low-level components that are going to be useful in the final program. So one sketch for this example, which looks a little bit complicated, looks like this. So what we have here is we're concatenating two things, and both of these things are what we call constrained wholes. So it's basically saying that there's going to be some program here, and it needs to contain at least one of these components. So we've managed to give the system a hint here, which is going to come from the natural language, that, all right, we're going to be repeating a number between 1 and 18 times. That's going to be an important concept to have here. But we leave the structure a little bit underspecified, right? So we're not trying to commit to fully what the program is going to look like because the language is not specific enough to do that, and it doesn't necessarily correspond closely enough to the final program structure, because if the user knew the program structure, they probably would have just written it themselves. So this is also a tool or a representation that we're going to be able to do search in using this program synthesizer. So that's the other key property of what's going on here. All right, so just to quickly go through how the stages of this model work, the translation from natural language to sketch basically looks like semantic parsing. And so we have two ways of doing this. One with a deep learning, basically LSTM seek-to-seek model with attention, and the other way using a grammar-based method that basically runs a semantic parser and produces a sketch that way. So these are relatively simple techniques. And the only reason they can work here is because this problem is much more tractable than trying to produce fully specified regular expressions. We've kind of broken it down into this step of interpretation that's much simpler, so we don't need some crazy powerful model and a ton of data in order to get this. And then training, I'm not really going to talk about. We have ways of deriving supervision heuristically from labeled regex data, and we also have ways of doing this with reinforcement learning. All right, and then finally, the program synthesis piece. basically what we do is we take the sketch and the examples, we start from the sketch, we start essentially expanding that and checking for consistency with examples, and then at the end of the day, we hope to be able to get the final correct program that's consistent with examples, and then the system is going to terminate. And one key thing here is that we actually take several sketches and feed them in. So we even build in another layer of uncertainty beyond just the fact that the sketch is inherently underdefined. We also try different structures and can simultaneously search over expansions of all of them with the synthesizer. All right, so we looked at 3 different data sets of English descriptions paired with regular expressions. So on the first of these, which is the data set from Locascio et al., we compared against 2 baselines. The first is their seek-to-seek deep regex model, and the second is a version of their model augmented with examples. So remember that we're using examples of the input-output, and they're not. So what we did was we took their k-best lists and filtered them, basically go down until you find one that's consistent with examples as a kind of re-ranking heuristic way of doing it. So our method works a little bit better on this data set, but when we go to a smaller data set from earlier work by Cushman and Barzilay, we actually see bigger gains, and then when we look at the Stack Overflow data, these deep regex methods actually can't transfer at all, while the sketch method is at least able to get enough out of the natural language for the program synthesizer to work for the rest of the task. All right, so critically, as we go from left to right here, we're going from having big kind of labeled data sets and sort of a narrow domain to noisier set data sets where we have a broader and broader domain. Users are trying to do more and more different things, and the data is collected more realistically. So we can see, again, the benefits of this approach, even looking at just the NL-Turk data, this big data set in itself, by looking at restricting the data on this data set. When we're kind of over here on the left side, these grammar-based and sketch-based methods tend to look a lot better. But if we look at the whole data set, it looks like, oh, well, we've basically solved the problem with a seek-to-seek model. What's the need for anything else, right? So the critical thing for this setting is that we need to be able to handle all these unseen types of regular expressions and things like that. And so we need a model that's flexible and can do that. And that's what our abstractions allow us to do. So the takeaways here are that this sketch abstraction provides a way to mitigate noise, basically, in how we interpret the language. We sort of sandboxed that off so that we can tackle these really complicated problems without having to think about collecting huge amounts of data for this task. So the other thing I like about this is that having abstractions and refining them is a core element of having programs and doing programming. And so in this case, it's a nice way to integrate examples into this framework, which is sort of the right thing to do for this particular problem. And so another benefit of doing things in this modular way is that we do have this natural interface for interacting with the user, which a lot of the times, if we just have an end-to-end deep learning system that outputs an answer, we don't necessarily have a real hook for the user to say, no, that's not quite what I want, and for them to kind of work with the system toward refining it. OK, so I mentioned it would be nice if we had big data. So we are currently trying to scale up some data collection for this task, and so that we can deal with some of these more interesting linguistic problems, like the really complex referring expressions and things like that, where I think there's a lot of interesting work to be done. All right, so that basically brings us to the end. I'm just going to briefly touch on a couple of other applications before we conclude. So one other thing we've been looking at are these so-called multi-hop question answering data sets, where in order to answer this question, you actually need information from 2 sentences in this supporting passage here. And so what we've been looking at is whether there's an intermediate abstraction that basically reflects a kind of reasoning chain or some sort of semi-interpretable sequence of either sentences or predicates or something that allows the model to go from things in the question to the actual answer. And so we've been exploring approaches where we sort of do some extraction based on this and then use a BERT model to actually produce the final answer. And so the real underlying question here is, what's the right way of thinking about how we structure reasoning to do question answering? And if we do that, can we get something that works more generalizably than models that just basically use an end-to-end neural net? And then finally, we've been looking at things for similar things for summarization, where here we have a two-stage process where we extract content and then use some kind of syntactic compression techniques, which again give sort of more flexibility and more controllability, and also break our dependence on having really nice labeled compression data that some deep learning models assume that we have access to. All right, so to wrap up, so when we're talking about low resource settings, I think it's important to realize that it's not only that we may not have data sets that are the size that we need, but they also might be confounded with these factors like topic or annotation artifacts that are difficult to disentangle. So sometimes our fully end-to-end neural approaches are not going to work well here, even if they build kind of robust representations that should work for a lot of problems. And so what I'm advocating for here are abstractions, which can help impose inductive bias and prevent us from fitting these kinds of annotation artifacts. They let us isolate components of our model, which we can then transfer across different domains. And finally, they let us kind of do a little bit of interpretation of what our model is doing. We can see these intermediate results and interpret them and figure out which component messed up. And we found this is much easier to kind of understand and get our hands into what the models are doing than when you're just looking at the final output of a big end-to-end thing and kind of scratching your head. So I think this is a framework that can work well for a lot of problems, and so we're really excited to pursue it further. And with that, that brings me to the end of my talk. I want to thank all my students and other collaborators at the UT Austin, as well as our funding sources. And all the preprints and et cetera are available on our website. Thank you. All right, and I guess we have time for a couple questions at least. Hi.
Thank you for the talk. So I have just one question. So the research that you've presented seem to all anchor on some predefined categories, for example, Wikipedia categories, or predefined formats, or scaffold, whatever you call it. So those still require human annotation. I wonder if it is possible, or there are already line of research or opinions that in your head that's about a model figuring out all the categories by itself. For example, if I were a kid, nobody tells me about any pattern. I'm given a basket of blue balls and red balls, and I know how to separate them into two parts. So I wonder if you could comment on this line of,
Yeah, so I think that's a really good question. Like, where do we, does it always make sense to assume that we have access to these things, and where do we get them from? Are they sort of bespoke for each task? I don't have a fundamental answer to that. I do think that there's a certain amount of, if we think about doing kind of more and more complicated question answering, there's going to be a point where fully end-to-end frameworks, I think, start to break down. Or at the very least, we need some kind of symbolic reasoning going on there. So we're going to need some kind of representation of either meaning or semantics in these kinds of cases. And so I don't know exactly what that's going to look like for every problem, and I don't know whether we're going to be able to induce that somehow, or whether it's going to be able to, or whether we're going to have to kind of label it up in each case. So I think that in my mind, the relevant answer to your question is stuff on kind of inducing discrete structured representation. So there's been nice work on things like vector quantized VAEs and things like this, where maybe we can kind of take those representations and project them onto things that we do understand and sort of post hoc analyze our models. You could also do this in the fully end-to-end framework without necessarily having discrete pieces in there as well. But you're right, that is definitely a sort of shortcoming that we want to address.
I see. Thanks a lot.
Go ahead.
Hi, this is actually a related question. So you mentioned about disentangling the representation. So trying to see, can you elaborate on that? Is it along the lines of the disentangled representation in the vision community, the beta VE type of unsupervised disentanglement? Exactly what you mean by, disentangling representations, yeah.
Yeah, so I think when I said the word disentangling, I was talking a little bit, well, maybe about how sort of some of our data sets have confounding variables. So there was actually a very nice paper I saw in arXiv just like 1 or 2 days ago about doing this for topic in various settings. I don't remember exactly who it's by, but I think the key thing here is just that like we realize now that our deep learning models are really just able to overfit the crap out of like whatever we put in front of them. And so I think we need ways of saying, all right, what we care about here is these are sort of these particular aspects of the problem, but I don't want you to just assume that like for NLI, because you see the word not, that it's automatically a contradiction, right? I guess that's the kind of disentangling I mean. And so when we have these kinds of abstractions, sometimes we can avoid having to fight those battles essentially because we've structured the problem in a different way. So I guess by getting back to the point about disentangling, like I think we need a kind of understanding of what's getting learned at these different stages or some kind of hooks into it just so we can partially assess how effectively we're learning all of those things and make sure we're learning the right stuff.
Okay, yeah, thanks very much. There's actually some related work from MIT. They're actually talking about deep learning using non-robust features, I think is also very related. So we actually want the model to actually learn robust features instead of non-robust features with some of these like spurious correlations, yeah.
Okay, great, thank you.
I think we are out of time, sorry.
So you've been thinking about this for a while.
Yeah.
Testing?
Okay, yeah, there we go.
Thank you. So you've been thinking about these abstractions for a while. I'm wondering if there are others in mind that we ought to be considering. Is co-ref a useful intermediate thing to work after, or what else might be abstract tasks to look at?
Yeah, so I guess what I'm sort of advocating for here is like if we're going to solve a complex problem like question answering, we can train end-to-end models, and I think there's a point where those models are going to keep working, and then I think eventually we're going to hit a point where we're just like not able to induce the super complex types of symbolic computation or reasoning that we need to solve all the cases of these things. And so I think, like if you look at something like the drop data set from AI2, where they have these sort of mathematical reasoning examples of question answering, what people do is they kind of bolt on, there have been several papers that do this recently, like they bolt on a sort of numeric reasoning layer in order, like kind of customized to this task. So I think models are going to need to think about stuff like coreference. I think that is going to be part of it. I think coreference is sort of part of the standard NLP pipeline, and so it's gotten a lot of use in neural net models already. And so I think that's a kind of fairly low level of this process, and so people are already using that. I think what's going to be needed is to build somehow even more on top of that if we want to solve really complex problems like, super sophisticated question answering examples or kind of understanding and summarizing a book, things like that. We're just going to need more sophisticated representations and a lot more of them. So,
thank you. All right. Thanks. Let's thank the speaker again.
Okay, thank you.